Algebras.
Thank you very much. It's a bit difficult to know what to say to a mixed audience like this, whether to just plunge in and lose half the people straight away or to start from the beginning. And after some thought, I've decided to start from the beginning. That means that largely the finite dimensional algebras get jettisoned, and this will be very heavy on algebraic groups and light on finite dimensional algebras. So I apologize in advance for irritating the experts. I also apologize for irritating the non-experts who will not get enough detail to make this comprehensible. So anyway, let's start, as I said, we start at the very beginning. K will be an algebraically closed field. And we start with her all-embracing majesty, the general linear group, GLNK. And we have the coordinate functions. And the xij, G is the ij entry of G, and the determinant function. Now, GLN has its algebra of regular functions, a coordinate algebra. That's the algebra on the coordinate functions, and the inverse of the determinant. So a set Z in GLNK is closed if it's the zeros of some functions in the coordinate algebra, some regular functions. And then a linear algebraic group will be a closed subgroup of some GLN. It too has its algebra of regular functions, its coordinate algebra, which are just the restrictions. And so a morphism of algebraic groups, well, first of all, some examples. SLNK, that's the set of zeros of D minus 1. The set of diagonal matrices. That's the zeros of xij, where I is different from j. That's called a torus. And UNK, the group of unipotent matrices, and that's the zeros of xij, where I is greater than j, and xii minus 1. So those are three key examples of algebraic groups. So though I'm starting from the beginning, I hope to get to some recent surprising and deeply disturbing results which have appeared in the last couple of years. That's my goal. So I hope you'll all be suitably disturbed by the end of the hour. So a morphism is a group homomorphism such that whenever I have an element of the coordinate algebra of G dashed, that implies that doing phi and then F is an element of the coordinate algebra of G. Right, what else have I got? Well, I've got multiplication on the group. And this induces a diagonal map on the coordinate algebra to the coordinate algebra of Kg tensor the coordinate algebra of Kg by the rule that delta of F is the sum Fi tensor Fi dashed if F of any product is the sum Fi G Fi H. Now, this makes the, oh right, for example, we have these coordinate algebras on GLN, and you see that this is the sum x I t tensor x t I tj. So that's just in disguise the rule for multiplying two matrices together. That's what that is. Anyway, this dual, the dual space is an associative algebra. Where the product is given by the diagonal or co-multiplication, and it has an identity epsilon epsilon of F is F of 1. So typically, the coordinate algebra is countable dimensional. So this Kg star is an uncountable dimensional algebra and unfeasibly large to do anything much with the whole thing. But the point is, it contains lots of stuff that you want. There is the Lie algebra sitting inside of here. This is the space of distributions such that x of AB is x a b1 plus a1 xb for AB in Kg. And this is actually a Lie subalgebra. Of the associative algebra viewed as a Lie algebra in the usual way. That is, the bracket is xy minus yx. And you can do this very explicitly for the case of GLN. So, for example, if G is GLN, then the Lie algebra is, well, you won't be surprised to know that it's GLN. Little g this time, with this bracket operation. And if G is SLN, you won't be surprised to know that the Lie algebra is little sln, which means the trace zero matrices. And when you've worked out these two examples, it's not difficult to work out the general Lie algebra of an algebraic group that somebody might throw at you. So let's move on to representations now. So I don't want to consider all representations, but the ones which reflect the structure of G as an algebraic group. So there's a name for that. A representation GL big NK is called rational. Just if it's a group homomorphism, if it's a morphism of algebraic groups. What this really means is that the map from G to rho G, and then you take the any entry, say RS entry, is a function in the coordinate algebra of G. So if we were doing this with K being the field of complex numbers, we shouldn't take complex conjugation. That's not a rational operation. And so that's a representation, but we might as well talk about a module as well. The KG module is called rational. If a corresponding representation is rational. Now, if I start out with a G module, a big G module, well, G module will now mean rational. Then it's also a module for the Lie algebra. So this works like this. If you have a basis of B, then multiply by a group element, then when you pick out the jth coefficient, this is given by a function in the coordinate algebra of G. That's the definition of what it means to be rational. So you define x vi sum x fji vj. And that makes V into a little g module. Let's write it as just the restriction, V as a little g module. Right. So let's have some examples of this. Well, I could start with GLN itself. I could take E to be the space of column vectors as a G module, then the familiar operations that one does to E result in rational modules. For example, the exterior and the symmetric powers are rational. So is any tensor product of these. And rational modules are closed undertaking submodules and quotient modules and tensor products and duals. So it's a very nice category. 2, let's look at SL2. So if I write an element of SL2, I'll write it as a matrix A, B, C, D. Now G acts on the polynomial algebra in 2 variables as algebra automorphisms. G of x is ax plus cy. G of y is bx plus d of y. So it acts on the polynomial algebra in 2 variables by algebra automorphisms. So it preserves the decomposition according to degree. The whole thing decomposes into its homogeneous parts. ER is equal to polynomials in x, y, homogeneous of degree R. Now, if we're in characteristic 0, this is it. If the characteristic of k is equal to 0, this is a complete set of irreducible modules. That's not true in characteristic P. But every one of these VRs contains a unique irreducible module. A unique irreducible submodule. LR. Well, you can see this easily if, for example, if, well, you can see some submodules anyway. Contains LP, kx to the p plus ky to the p. And now these modules form a complete set. Set of irreducibles. And you can say very explicitly what LR is. And this interacts with the finite group theory in a very nice way. If I replace this algebraic group SL2 over K by SL2 over a field of Q elements, I still get a complete set of irreducibles. Well, this was known to Brouwer, in fact. But it holds much more generally in the context that Olivia was talking about this morning. For semi-simple groups, semi-simple, simply connected groups, just say groups. And that is a theorem of Steinberg. So that means that even if you're interested in the finite groups, it's a good idea to look at the algebraic groups where you have these other techniques, like there's a very nice cohomology theory, there's geometry, there's the Lie algebra you can throw at it. And like Chris Parker, I feel the need to quote from Ellen's talk at this point. Just get the words right. Yes, most finite simple groups are of Lie type. So this theorem of Steinberg is extremely powerful, even if you're interested in finite groups. Right, there's one other case that I need to consider. This is where I take the torus, Tn. Remember, this was the group. And here I have homomorphisms labeled by an n-tuple of integers. And I have a group homomorphism to the multiplicative group of the field. A1 to the lambda 1 up to an to the lambda n. So let's put x to be xtn to be the set of all these lambdas. So that's just set to the n, in other words. And then for a tn module, you have the weight space, V lambda, which is a set of V and V, such that TV is lambda TV for all T and T. This is called the lambda weight space. And you say that lambda is a weight if the weight space is non-zero. Now, every Tn module decomposes as a direct sum of its weight spaces. And so one wants to keep track of these weight spaces, and there is a device for that. It's called the character, the formal character. So you form the integral group ring. Zx, it's got a basis, a z basis of elements e lambda, the formal exponentials, and multiply according to the rule e lambda, e mu is e lambda plus p. And now the formal character is the element which records all the weight space dimensions. And yeah, okay. Leave it at there for the moment and move on to reductive groups. Now I'm going to assume my groups are connected unless I say something else. Connected. So G is an arbitrary group, and G has a maximal, normal, connected, unipotent. Now, unipotent means it's a subgroup of one of these groups that we've seen already. A unipotent closed, probably say some words twice if I'm not careful. Normal connected, and it's denoted RUG. It's called the unipotent radical. And G is called reductive if the unipotent radical is trivial. It's semi-simple if there's no non-trivial, closed, connected, normal, solvable subgroup. So, for example, the general linear group is reductive. And the special linear group is reductive but not semi-simple because it has a center. SLN is semi-simple. Now, attached to a semi-simple group, there is a root system. And probably wisely, Olivier decided not to attach this root system, but I'm going to give it a go. So let's see how this goes. Well, so we attach a G is going to be semi-simple. And we're going to attach a root system. Because this governs the representation theory to a huge extent. So you choose T to be a maximal torus. Now here's a group which is, it's the normalizer of T modulo T. So this is finite. It's called the Weil group. So what do we do to attach the root system? Well, we have the Euclidean space. Well, not yet. We choose on E, which is R tensored with xt. So that's free. This was a free abelian group, so this is some R to the n. A W invariant symmetric non-degenerate have I left anything out? Bilinear form. So that makes E into a Euclidean space, and then we have inside that the set of roots. Phi will be the set of weights, non-zero weights, of T acting on the Lie algebra. Yes, I did. I knew I'd left something out. Thank you, Dave. That was just to keep you awake, though. Positive definite. Thank you very much. Right. So the set of non-zero weights of T acting on G. The conjugation action of T on the group descends to an action on the Lie algebra. And then E together with phi is a root system. So now we can impose on xt a partial ordering. If I have lambda in and mu in xt, oh well, lambda is less than or equal to mu if mu minus lambda is a sum of positive roots. I didn't say that. We should have chosen a system of positive roots. Now, if G were GLN, which is slightly illegal because I said G was supposed to be semi-simple, it's not significantly illegal, but it's nevertheless, it's strictly speaking, it's illegal. And you have to make sensible choices for 5 plus. Then this is a partial ordering which Olivia mentioned this morning, the dominance partial order. So it generalizes that, and now there is the set of dominant weights. This is the set of weights such that the inner product is non-negative. All positive roots. Now you've seen how the irreducible modules, the classification works for SL2. And there is a massive generalization of that, the classification of modules by highest weight. So that was certainly clear in the 1950s to Seminar Chevrolet. And of course, for groups over the complex numbers, it goes back much further, but it goes like this. For lambda a dominant weight, there exists an irreducible module L lambda with highest weight lambda. And these modules form a complete set. Form a complete set. Of pairwise non-isomorphic irreducible modules for G. So the big problem or at least, well, it's been a big problem for a long time. Really find the character of all lambda. Well, that's a ridiculously difficult problem, and I warn you not to try it. Don't try this at home. It will come to grief. Of course, I shouldn't say that. Lots of young people here who might have an idea which will completely transform the subject. Reminds me of what, if I can paraphrase what John Alperin said once about his, I think it was about his weight conjecture. Well, you can study some problem that your supervisor sets you. You can prove something slightly better than your supervisor. Get your PhD, spend the next 5 years wandering around on postdocs, trying to detach yourself from your supervisor's work. You can spend the next 20 years going through the gears, lecturer, senior lecturer, reader, professor, or you can solve this problem and immediately get your chair in Princeton. Anyway, it's going to get even more depressing, I'm afraid. Well, G is called simply connected if there exist the so-called fundamental dominant weights such that dual to the set of simple roots, where alpha 1 up to alpha n are the simple roots. For example, SLN is simply connected. And actually, as far as representation theory goes, you only need to look at the simply connected ones. The other ones are a quotient, so their representation theory is included in the representation theory of the simply connected ones. So there's absolutely no loss in assuming that it's simply connected. Okay, well, here is at least one finite dimensional algebra. This is the subalgebra of this unfeasibly large algebra, but generated by the Lie algebra. Its dimension is p to the dim g, and it has another life as the restricted enveloping algebra of G. So the simple modules for this can be quite easily parametrized. You take x1 is the set of lambda in x plus, such that the inner products with the simples is less than p, or alpha I simple. Then there is the theorem of Curtis, which says that to get all the irreducible modules for U1, you just restrict the simples L lambda. Form a complete set. Well, so that's restricted to G, I said. A complete set. Set of simples U1. Now, since this, well, it's the same thing. It's if you know the action of G, then you know the action of U1, and G is sitting inside of U1. Yeah, if you like, it's restricted to U1. Now, since this is a finite dimensional algebra, every simple module is associated with a projective indecomposable module. So since U1 is finite dimensional, for each simple L lambda, there is its minimal projective cover. Let's call that Q lambda. So that is a projective module whose unique simple quotient is L lambda. Section 4, counterexamples. There is a conjecture which became known as Humphrey's conjecture, Jim Humphreys. Which is that every one of these projective indecomposables admits the structure of a G module. I.e., there exists a G module, let's say Q lambda twiddles, such that the restriction lambda is Q lambda. Now, the group acts on the Lie algebra by conjugation, and so you can twist one of these by a group element, and you always get the same Q lambda. So it's tempting to believe there is a G structure which is accounting for that. Also, this theorem of Curtis says that every simple module for G is the restriction of a module for the whole group. So this has been around for a long time, certainly since the 1960s. And, well, in 1990, I attempted to strengthen this conjecture. Since it couldn't be proved, I made a stronger one. So I nominated a particular G module. G module. Q twiddles lambda. Whose restriction is Q lambda. Well, this Q lambda twiddles was supposed to be a certain tilting module. I probably won't have time to explain what that entails. And I should say that this was, at least it was at the time, and subsequently was consistent with all the known evidence. For example, if p is greater than 2h minus 2, this is a Coxeter number, which is, for example, n if G is SLN, then it's true. And that's really due to Janssen. That was Janssen's argument was pre-tilting, but his argument certainly demonstrates this. But now we have one and only one counterexample so far from 2019. Bendel, Nakano, Pillen, and Sobaji. It's false for the group G2. P is equal to 2, and lambda is the weight 0. So it's just by an explicit calculation. It's not difficult to get your hands on the tilting modules, and then you have to worry about how they restrict to the little g. But of course, it doesn't answer Humphrey's question. So if you do want a problem, I would say we need more counterexamples. Of course, that's not a very glamorous thing to do, but certainly it would be useful. And also, this doesn't settle Humphrey's conjecture, because that might have nothing to do with the tilting module. So, you should settle Humphrey's. I would be very surprised if Humphrey's conjecture were not false in exactly this case. It would be strange if there was some exotic structure on Q lambda which is not apparent from what has been seen already. So that's a bit of a blow, but there's an even more serious one coming up. This, of course, that was of great interest to me because I was interested in this back in 1990. But one which has attracted a huge amount of attention is Lustig's conjecture. He says that if P is bigger than the Coxeter number, then the character is given, well, in terms of Weil characters, but by explicit, is given explicitly by Kazhdan-Lustig polynomials. These were invented, I understand, to handle the analogous situation for complex Lie algebras and high-weight representations where they were brilliantly successful. This is known if P was very large by a long paper by Anderson, Janssen, and Sergel, I think 1990. Later, with an explicit bound by Fiebig, which for SLN, it's P bigger than n to the n squared, which means that if you're looking at the group SL4, this only we only know that this kicks in if p is bigger than, here we go, 4, 294, 967, 296. And of course, the case SL4 can be done. One can find the character in all cases using old technology due to Janssen. But still, everybody thought that it must be true. I mean, you know, Lustig said it, so it's probably true. But then, bombshell, Geordie Williamson, he says that p greater than n log n is definitely required. In type A. And he proves that in a paper which sounds like the first chapter of the orange book of Lustig that we heard about this morning. Torsion in stalks of integral intersection cohomology of Schubert varieties. So where do we go from here? Well, there are lots of papers which say things like, if the Lustig's conjecture is true, then blah, blah, blah. Perhaps we should now more modestly, instead of trying to get something that works for all sufficiently large primes, take one prime at a time. If anybody has a beginning research student, you could set them working on the case p is equal to 2. And if they have a second research student, you could try p is equal to 3. Okay, I'll stop there. Thank you very much.
It's open whether it satisfies Humphrey.
Yes, that's right, that's right. I mean, naturally, I've tried to do it. I've taken their work and kind of looked, but it gets very, very complicated just to try and see if you can persuade yourself that there is no structure on this. I mean, it's quite a big module. I forget how big, but it's got a reasonably long composition series. And yeah, so that's one thing to do. The other is just to find more counterexamples. If you had a counterexample for an for every n, well, that for n sufficiently large, that would be really nice.
More questions? In that case, we should thank Steve again.